Shall we start? I think we'll start, then we'll end soon. Yeah. So okay. So now we started with this architecture. So from like I have plenty of slides, but we are just going to touch the, you can say, the only the important ones, only to give you the idea about the thing rather than discussing all the results. Okay. So here we discuss about this architecture, the motivation behind this, and in order to develop this as a tunneling device, we just checked its Venn diagrams, and we found that there were like tunnel barriers on both sides. Okay. So to check the effect of drain doping, we also varied it, and we saw that this negative portion that you will see towards the negative portion, the bipolar current is reduced when you selected lower doping concentrations. Okay. So this is what has been discussed. Like the drain doping should be reduced so that you can have lower ambiguous current. Right. We're not going to discuss these things in detail, and we're just going to go into the most important like parts. So this is another one. FinFETs. That FinFETs are like the 3D structures where you have the fin shape and then you have the gate wrapped around on all the sides. And we tried to get this once the ribbon FET was announced. We tried to take that device and try to simulate it, right? Because that is how we understand the performance of new devices. You do not get all the results that Intel would have given us. So therefore, we wanted to check how this device performed. And in that case also, we tried to introduce a dual core, you can say source drain, so that this doping concentrations can be varied on the outer core and the inner core, and just to check its like performance. Okay, this was just a random structure that we did, but we had some interesting revelations. And one of the most important thing that we discovered is that since this is entirely silicon, like the body is entirely silicon, so we are not like we do not need additional costs in the fabrication line. That is the first point. And second point is that by changing the doping concentration on the inner core and outer core, we were able to see the change in the electric field profile and the effect of the gate valve function and all this stuff. Okay. So more than a device which was directly aimed for application, this was actually designed to study the properties of the ribbon FET. So the ultimate objective was not to directly use it in circuits or something like that. We wanted to see that as gate all around FETs were announced by Intel and Samsung simultaneously, we wanted to see how these devices would perform if they were modified. Okay. And the calibration was basically done based on a gate all around structure which was reported by some researchers. Gate all around MOSFETs they called it. So that became the basis for the calibration of this device. And this is, I think, the most important part of this entire, you can say, slide with reference to this FDP. Because results you will get, if you are simulating it properly, you are going to get the results. So I'm not going to discuss about the results. I'm going to discuss about how to set up the simulation environment. Okay. Now, if you observe, this is the fin that we are talking about. This is the fin. I have eliminated the gate and other things from this picture. Okay. So you can see only the fin where you have the inner core and the outer core. Okay. Now, the problem with this is that whenever you are building your structure, a 3D structure in an industrial environment, you normally get a very default option of placing your cortex. Okay, either you can place it here, you can place it here, you can place on all the four sides. Okay, but depending on the nature of this device, it would have been okay if we could have placed the contact on only one side. Ultimately, you only need the electric field, right? So that if you put the contacts on both sides of your fin as source and drain, so basically it should work. And normally it works, but there is a problem. The problem is that if you observe, you will see that in the source also there is a linear variation in the potential. Okay, But basically, if you are placing a contact in the source, the potential should stay constant because you are applying the same potential there, right? But we observe that if you place your contact only on one side, then you will observe this kind of linear variations in the source and drain. So then we discovered that if we are simulating such kind of architectures, then we'll have to go with contacts on all the sides, available sides which are present. Here, this side, bottom side. Okay. So then it is going to give you a linear potential. Okay. Now the question is that why do we want a linear potential? Means it's okay, right? I have placed the contact. It gave a you can say why we do not want a linear potential. Why we want a constant potential? It is okay, right? I have placed the contact here. It is giving me some kind of potential. I am getting the current. There is no problem. The ultimate objective is to observe the current. But remember the equivalence of simulation and modeling, right? Which we discussed. So if you are applying a potential in your source in a device, it is treated to be constant in your throughout your models. So I also have to look into that because if someone takes this device up for modeling, then he will not be able to replicate the results which I get with a linear potential. So it will become very difficult for him or her to model this device. Are you getting my point? I could have left the device at that stage itself. Even if it had linear potential, I could have left the device because I was getting current. There was no problem with current. But the problem is that modeling that if someone takes this device up for modeling, then he is always going to start with a constant potential in the source up to the depletion period. So then it will be a problem for him. He will have to again standardize these things for creating a linear potential. Okay. So therefore we try to keep the thing simple so that if we report it, then even others can also use this data. So therefore we went for contacts on all the sides. So I'm getting my point. Both the results are correct if you are looking at it from the perspective of simulating a device. You only need the performance parameters. Both the devices are correct. Okay. But if you are making it available for someone to model this, then it is better if you try to keep the device with a constant potential so that it becomes easier for him to model your device. After that, he can do anything with it. He can create a linear, you can say potential, he can do the drain current analysis, and then he can proceed. Okay. So this is one part which I think is very important whenever we are defining context in our simulation. Means you normally do not always go with observing whether you are getting a current or not. You also have to check whether your intermediate electrical parameters are also okay, whether they are following the normal convention, the normal approximation. Okay, clear? Am I able to reach out? So these are some results, and this is how a calibration curve looks like. Okay, you have simulated the device. This is from your simulated platform, and this is your experimental data. Okay, so actually, when you get this, for example, you get a device which you are going to calibrate. So you take the device, you are going to create the exact device in your simulation platform, and then you are going to tweak with the models so that you get a match between your experimental data and simulated. Once this is fixed, you proceed with whatever constants you have kept for those models, and then you apply them in your simulation. Okay. So one more important thing, for MOS based devices, you will always get this kind of very perfect calibrated curves in industrial simulators. Wherever there are like MOSFET based operation devices which work on MOSFET principles, like FinFETs, MOSFETs or vertical FETs, there is a high possibility of getting such beautiful matching between simulation and experiment. But wherever there are other non-conventional, you can say models like TFETs, then you will have some kind of mismatch between simulated and your experiment during the calibration. Okay, and that is very well established. Although there are many articles where you will find the exact match, but most of them may also be having some parameters which they were actually not supposed to tweak. Okay, for example, you cannot tweak the band gap of a material, right? Because it is constant. So therefore, while also selecting calibration techniques, you need to see which parameters they have varied, whether it is a material dependent parameter, whether there is flexibility of varying it, or they are just varying it just for matching the curve. Okay, so that should be kept in mind whenever you are going through articles where calibration is discussed. So this is the calibrated, you can say, graph for this entire simulation, and this is how the electric field profile looks like. And yeah, we did analysis by going through the different cross section of the device to understand how the electric field profile varies. So we took the we tried to check the electric field exactly in the middle of the device, and we got this kind of characteristics. Okay, just observe the two characteristics, and this one is when we took at the extreme end of the device. So this is for middle, this is for extreme. Now the most interesting part is if you are in the middle of your device, so you are distant from your gates. Okay, there are equal distance from both the gates. Okay, now as you move away from the gate, the control of the gate is also reducing. So your electric field will also reduce as you move away from the gate. Okay, the vertical electric field. And when you move towards the surface, this we call as the surface near the gate. So then you will have influence of the gates, the adjacent gates which are present, and then you will have steeper, you can say this pointed electric fields both towards the source and the gate. Okay, because you are closer towards the gate, the influence of the gate is more. So you can see this kind of a plot. Okay. Yeah, this is one work which we are doing. Okay, this is not yet this is not yet sent for publication, or we are not yet done. I'm only showing it here. We tried to place metal blocks in the entire fin. So you have a fin structure. Okay, suppose this room is your fin. Okay, fin is a 3D structure. This room is your fin, and all these benches are your metal blocks which are placed. Okay, so we just tried to put the metal blocks and tried to see how the profiles vary. Okay, just did it randomly. We don't have any objective in mind. We wanted to see how it varied. If there are metal blocks inside a fin, then how the results would look like. So that was the objective. Okay, and if you observe, this one is without metal blocks inside. This is with metal blocks inside, and then we try to see those portions where these cut lines are present, where these metal blocks are present. So what do you see? This is without metal blocks. This is with metal blocks. Okay. Interestingly, you will observe that if you do not have metal blocks, your electric field will be normal. It will spread out through your entire device. Okay, but if you place metal blocks, it will like steal the electric field from the surface and will concentrate around itself. Okay, it is just acts like a magnet for the electric field if it is placed inside the fin of the device. Clear? I'll show you some other, you can say this is for absolute electric field, this one is for potential. So you can see these contours are just surrounding these metal blocks, but here it is spreaded uniformly throughout the device. This is without metal blocks.
You have been able to localize the fields.
Yes, this is the localization of fields around the metal blocks. I'll tell you the importance which we discovered, like where these things could be used. Okay, and I'm telling you after showing the results here. So this is for electron mobility. So the mobility also gets very well localized in those particular regions. Okay, electric field localization and surface potential localization is okay, but mobility localization is an interesting, you can say, revelation, because normally we do not talk about mobility localizations. Okay, so this is one of the, you can say, things that we tried just randomly, and we found these things. Now the point is that possibilities where this thing can be used, we are still in the process. So basically, whenever we are talking about defects in semiconductors or traps in semiconductors, so most of these traps can also be metallic particles. Okay, now if these metallic particles are located in the bulk of the device, so this may be the scenario, like they can create this kind of localizations within the fin or within the, you can say, bulb, and then they can steal the electric fields and surface potential from the surface of the device, because that is where we need maximum electric field so that we can have more currents. Okay. Another point which we thought, and I think it would be very, very applicable, even you can pursue this. This is an open problem, so we do not restrict things like this. So if you wish to take up, you can take up. So another thing is, you have corner effects in this kind of sharp structures. Okay, and in gate all around structures, since towards the side you have two, you can say, gates, so at the point you have very high electric fields, and it degrades the, you can say, oxide dielectric in that particular region, and also the semiconductor there, right? Now if we are able to somehow place these metallic particles somewhere around the corners such that it steals the electric field from there, so then maybe this may be one of the, you can say, possible theoretical solution for understanding or mitigating corner effects. Okay, so this is in a very nascent stage, like this is only a theoretical one. So this is one observation that we got. Okay, so now let's go into the modeling part, because the title also says modeling and simulation of emerging electronic devices, right? Here we went I went for designing a circular gate. Okay, circular gates were somewhere popular around 2000, most probably around 2015 to 18, where they started with the omega gate shaped structures, which they presented at IEDM. Okay, it was probably from Intel or IBM, and from that motivation, we took this circular gate structure and we tried to model it. Now, modeling a very conventional structure, you already have lots of papers, lots of articles and insights into that. But no one had done this kind of, you can say, architectures where you have a circular variation of the electric field, vertical electric field. So if you observe towards here, the thickness is small. This is the oxide. This entire circle, semicircle is the oxide. Here the thickness is less. As you move here, it will start increasing, and again it will start decreasing on this side. Okay, so this is the nature of this entire electric field profile. Now when we start with rectangular structures, you have very set conditions. Okay, you start with the Poisson equation, then you apply your parabolic or quadratic approximation, then boundary conditions, then surface potential. Okay, now here you cannot do that. And if you do that, I am showing you what you are going to get, what results you are going to get. And without doing that, and by applying the technique which we use, what results you are going to get. Right? Now, in order to do this, the first thing that we did was, we are very comfortable with rectangular structures. Therefore, we divided this entire thing into large number of rectangles so that we can apply the Poisson's equation in each block. Okay? Right? So, and we were very happy that we are able to do this, and there is very lesser variation, like between the actual results and our results, the initial results values. But when we plotted the entire surface potential, so we could see this part, right? So the line is the simulated one, which is the calibrated one. We are matching our model with the calibrated simulation one. Okay, so we want to match our model with this black line. Okay, and we, first of all, we simply divided it up into this. We applied the Poisson's equation and boundary conditions. We found this level of inaccuracy in the model. Okay, then the next step. Now you don't know what to do, because you have done everything. You have split it up into rectangles. You see that your values are matching here and here. So you do not have anything to do. There were only some random variations that you can check in your models, right? Then we discovered that instead of taking rectangles only throughout your system, instead of taking only rectangles and applying the boundary condition of these rectangles, you'll have to split your structure into two parts. First part is this, second part is this, for taking the boundary condition only. So there was a difference in the boundary condition, due to which we were getting this inaccuracy. Okay, so then we inserted the boundary conditions for both the structures, and we got this match, the red one and the black one, which is our model. Okay. Secondly, that was solved. We first started with SiO2, which is a permittivity of 3.9. So that was solved for us in the first instant. But now we have to validate our model for higher dielectric constants. We went for it, and then we also checked for higher voltage. And at higher voltage, it was giving this level of inaccuracy. So it means that whatever boundary conditions you have developed, those do not apply at higher gate voltage. So it means now I have to tweak the condition for the gate voltage. And then by observing some empirical, you can say, results from the simulation, we develop a single equation. And based on that, we were able to suppress this value and then get results for both lower gate voltage as well as higher gate voltage. Okay. So there were 2 points while doing this. First of all, non-uniform gate. So this was like nowhere there. So the first thing we did, the simplest thing, because we already have references to rectangular, you can say, modeling, I split it up into rectangles. Then we tried, but we found this error. After that, we went for boundary condition matching, okay, for two structures, and then we inserted it. We got this. So we were very happy because we had already developed the model. But now, if you are going to report this, you'll also have to show for other voltages. So when we went for higher gate voltage, you have this mismatch. So it means there was something in the gate voltage part where you have to tweak your boundary condition. So this was the second part that we did, and we got this. I'm not showing the equations here because I think the steps are more important than just showing the equations for this. So these were some of the failures and how the solutions came up. Okay, and these are the results that we showed. And we also developed. We also went for the drain current. And this drain current, we did not go with the standard, you can say, integration, numerical integration. We tried to go with the closed form expression by using approximation, and we got this match, okay, for the drain current. So this was how we did for the circular structure, right? Incomplete ionization, most probably I will skip that one now. Yeah, single traps. So So normally, whenever we are talking about this MOSFETs, we have the ideal phenomena and the non-ideal phenomena. Okay, ideal phenomena is like where we have all the things where we are very comfortable with. We can derive the equations, right? The ideal processes, drip diffusion, where we do not have any kind of disturbances in the movement of carriers from the source to drain. Okay. Then we have the non-ideal phenomena, which we normally do not take into consideration. Okay, non-ideal phenomena are those which must have or might have cropped up during your fabrication process, and where we tend to reject those devices in terms of understanding the average value of that fabrication unit. Okay, but these are also very important because a device may be very sensitive to some non-ideal phenomena, a single device, and another device may be sensitive to some different non-ideal phenomena. And the most common one that we see is the interface. The interface is like, you can say, the most luxurious part of your device. The interface of the oxide semiconductor interface is the most important part of a shrunk or a short channel device. Okay, so therefore interface studies is very, very important if we are talking about devices. And this was not in the picture until, you can say, 2015. After that, interface studies on devices have become very popular, especially with reference to interface traps. There have been interface studies for materials. From the material perspective, there were interface studies. For junctions, there were interface studies. But for FETs, field effect transistors, and the advanced devices, the interface studies became very popular in and around after 2013 to 15. Okay? And the reason for this is the analysis of the interface traps. So if you have defects in your interface, and when your device is very small, your gate length is very small, you have only few nanometers in your gate length, and out of those 1 or 2 nanometers are already taken by your traps, then the device performance is highly degraded. So therefore, it is very, very important to understand that interface quality of a device is one of the most important parameters for fabricating this particular fence. Okay. Based on that, we started analysis using single traps. Okay. So basically, the device simulators, they offer two kinds of analysis of traps. Okay. If you have an interface like this is a MOSFET, this is your oxide. So this basically is taken to be the interface. Okay, this basically is taken to be the interface. So simulators, they offer two options. One, you can directly define traps, and it is going to take the entire interface. Okay, all over the interface uniformly, the traps are going to be distributed, and this distribution is defined in terms of energy, exponential distribution, Gaussian, level. So these are the definitions. Okay, so physically, on a physical node, these are going to be uniformly distributed, but versus energy, they will be like in a Gaussian nature, then in a exponential nature and level nature, right? This is one option. Second option is single traps, which we are going to like see a few examples, and from here we are also going to see an application. Single traps. Why are single traps important? Because suppose if we are talking about TFETs, which we have done a few minutes back, you know that your junctions are very, very important, right? Your junctions are very, very important because here you have your on-step barrier and here you have your ambipolar barrier. Now, when you are defining your traps uniformly throughout your interface, now you don't know which part of your interface is responsible for which dominant mechanism because your traps are spread throughout, right? Are you getting my point? My first objective was to see the performance of my device under the influence of traps. That is successfully done. I can place interface throughout and then I can check. But now I want that since I am reducing my gate length each and every time, I want to see which part of my gate length is more sensitive to trap. So in that case, I cannot give out uniform traps throughout, right? I have to place a single trap somewhere here, then check, somewhere here, then check, right? So therefore, that is the interpretation of this single trap. So single trap allows you to place your trap exactly at the coordinate where you want it in your interface. And that is a very, you can say, very useful tool for understanding the sensitivity of a device. Uniform traps, research on uniform traps, this is almost like it has achieved saturation. People started in 2011 and now everybody is doing it. Okay, but single traps is one area where people are yet to explore. So single traps is a very important part, and single traps will give you more insight because here in uniform physical distribution of traps, you don't know which part of your gate length is responsible for the trap. But for single trap, you can put the trap at your desired location and then you can check. If you put it near the junction, how it is going to look like, how your drain current is going to look like, how your electric field is going to change. Here you are putting, then you check. So that is the, you can say, available facility that you have in this simulators. Okay. So therefore we took up single traps while understanding this device. These are the analysis. Single trap, just by definition of single trap, we placed the traps at different location in the device and check. Okay. Next was cumulative single traps. Cumulative single traps means suppose I have this interface. So first I will put one single trap, check the results. Then I will check for two single traps, three, and I keep on increasing. And then I will see which part is going to affect. Okay. And this is cluster of three single traps. Cluster of three single traps, I will go with clusters. So three here, next three here, these are going to go, then next three here, these are going to go. Okay? And finally, we have special randomization of single traps. Now, this step is very, very important. Now, since this was an unknown field, right? Not much people has explored this in industrial simulation. So, we don't know whether what we are thinking is correct is actually correct. So, you need some kind of validation, right? So, therefore, what we did, the best form of validating anything is taking a randomization. So that you just leave it on the simulator and then check whether it is giving the same results which you have done when you deliberately did it, right? So therefore we went for the randomization of single threads. So the simulator is not going to ask you where it is going to put. It is going to put it randomly in your entire device, and then you can check whether those results are in agreement with the ones which you have done. Okay, so for us it was perfectly okay. Whatever randomization they did, what the simulator did, the same kind of results we were getting for the three cases. Okay, so this is one strategy that we did for single threads, and these are some results. Maybe I will skip this because the next part is even more important related to single threads. Okay, just at the end, this was the randomization thing. We are showing here for 10 runs, and in the 10 runs, you can see the track position is varying at every run. So this is done by the simulator. This is not what we are doing. The position is done by that, and we can see the like how the BTBT, the bend-to-bend tunneling is changing in the device. Okay. Yeah. Now, this is one part which like is very dear to me. Not because like this is something we have done very great, okay, but because this is one part which industrial simulators don't have. Random telegraph noise is basically observed when you have single trap in your device. Okay, so even if you buy a MOSFET from the market and you just apply constant bias at it and just check the current versus time, you will see there will be some fluctuations in your device, in your current or in your voltage. Okay, these fluctuations that you see, these are basically random telegraph noise, and these are present there because of the traps which are located at the interface of your device. Okay, so we have also done this experimentally by looking into the normal MOSFETs which we have in our lab. So we have checked this, and there is also work going on predicting this through AI. Okay, so on predicting, if we can match something, we can just tell that okay, this device may have this much amount of random telegraph. So basically, this is already tested. So we tried to take this inspiration, and then we went for the industrial simulator part. So whenever you have single trap in your device, and basically it is said that you cannot have only one trap in your interface. There will be many traps, but at one point of time, only one may be dominant in different scenarios. Okay, and that is where this random telegraph noise becomes very, very important. Therefore, random telegraph noise is defined with respect to the number of traps. So, if there is a single trap, you will have two states. If you have more than single traps, you will have more number of states. But our modeling is limited to only two states because that is the basic form of modeling. Now, the motivation I am telling you, if you go into an industrial simulator like Centrus or you can say Silvaco, you will not find any way to introduce random telegraph noise. Okay, you cannot see random telegraph noise as a result in that simulator. You can go up to noise spectral densities. From there, you have to like decide. Okay, this has this noise, this has this noise, but you cannot actually model it. So what we tried to do, we tried to make it a very compatible model with the simulation, so that the simulation runs up to a certain point. We extract the data, feed it into our model, and it gives the random telegraph noise. Okay, so that was the basic idea of doing it. And these are the parameters. So you can see there are two blocks, the noise spectral density in TCAD. From there the parameters are extracted, and then we feed them to our RTN model, and then it gives you the nature of your random telegraph. And it looks something like this, the two-state random telegraph noise, where one state is actually the trap is capturing the carrier, so you'll get one state. It is releasing the carrier, you'll get the other state. So there are two states. If there is a trap at the interface, basically if you have a trap at the interface, you have an electron moving here, so it is going to capture this, it is going to hold it for some time and again release it. But you don't know when it is, at what instant it is going to capture and at what instant it is going to release. Therefore, this is a probabilistic, you can say, matter. Okay? So therefore, you have to go with like Poisson distribution process and everything to model this, right? You cannot have a definite predictive kind of a modeling if you are going for this single rand. So this is how it looks like. As I have said, capture and emission are the two very important terms that are associated with random telegraph noise due to single rands. Now I am going to talk to you. I am not going to talk to you about the results. Of course, I will show that. I am going to talk to you about the failure which we got in the beginning and what technique we used to overcome that. Okay. Now, whenever we talk about noise, so there are three different types of noise that you can noise models which you get in simulators. Okay. First one is the diffusion noise, generation recombination noise, and flicker noise. Okay. Random telegraph noise, as defined, they have a Lorentzian spectrum. Okay. It looks something like this, where this slope has to vary with inverse of f square. Okay, the frequency. And this is validated by only one kind of noise, which is your generation recombination noise. So if you go through the manual, you will find that only the generation recombination noise will give you this f square, you can say term. Okay, so which means that if you have to analyze your random telegraph noise in an industrial simulator, you'll have to select the noise model where you have the Lorentzian spectrum. Okay, so that is the first point. That is was the first thing that we did. First we analyzed the models and then we took this. Next, we had to develop an algorithm or a model so that from the from TCAD we are going to get this noise spectral density versus frequency. That is the only thing, the final point that you are going to get from your industrial simulator. But actually you need this. So therefore you have to build something in between so that it gives you this. Okay. So the first thing when we tried to do this, we extracted all these parameters. We extracted these parameters from this graph. There are a certain set of equations, and we got this. You can say RTN, but it was not correct. It was not correct. Like how do you know it was not correct? We tried for two different devices, and for both the devices, it showed the same result. So we went for the conventional tunnel FET. We also went for the NPN tunnel FET, and for both the devices, we were getting the same results. So then we again went back to the models, and we found that you have to set a definite value of the time constant, and that time constant is going to vary from one to another. And the only place of getting the time constant is if someone have done those tests experimentally or where you have those results. Okay, so had we not done for two devices, we would not have known that our results would have been wrong. So therefore, this is one of the techniques of doing, you can say one of the very simplest techniques of doing simulation. Whenever you are taking up a new device, you always run a conventional device for the analysis and models which you have done. So that at any point of time, you know that there has been some mismatch in between in the actual physics of the device, and then you can decide, okay, this is where I'm going wrong. Okay, so therefore we got to know about this, and after that we corrected it, and this is the algorithm. Okay, I'm not going to go step by step because I'll have to explain Poisson distribution process and everything. But the only thing that I want to tell here is that after doing everything, after taking the parameters, after doing everything, we were able to produce this from our model. Okay. Now, to a very means you can say to a person who is like who already knows signals, right? Like everybody of us have seen this kind of graphs. How are you going to convince him that this is the actual RTN that you have created? There should be some logic, right? I can create this like by putting some zeros and ones in my system, isn't it? So there should be some authentication of your entire process, right? So I am talking about the fraud that can happen, like how to detect it. So now I can produce this by any kind of code, zeros and ones. I can just write a stream and it will produce it, right? Now, therefore, what we did, that question was also there in our mind whether the algorithm which we have written, that is actually it has the properties of the RTN or not. So the actual property of RTN is that it will always follow an exponential pattern if you count the number of highs and lows. Okay, the number of highs that you have in your system, because you do not know at what point this is going to go and what point is going to come down. So these are very random instances in your profile. Okay, these instances are not given by us. These are given by some random number units which you have, which is present in your model. So you do not know when this is going to go high, when this is going to go low, and for how long it is going to stay. It may be something like this. Okay, so I can create this graph by any kind of code. So you should have some authentication. The only authentication for random telegraph noise is that if you count the number of ones and zeros, is the highs and lows, it should always follow on an average an exponential pattern. Okay, we check this, and after checking it, we also verified with literature, because you can see here there are some peaks which are going up and some peaks which are going down, right? So perfectly it is not exponential, but we saw from experimental data whether they have got similar kinds of patterns, and yes, these were there. So we could confirm that the RTN that we are doing is actually following the actual process. Okay. After that, now if you observe this method that we developed, we started with TFETs, but we realized that this can be applied to any device. Okay. We realized that this can be applied to any kind of device, because here you do not have any one parameter which is only unique to TFETs. You are just simply extracting the noise spectral density, and after that you are extracting the parameters and you are getting this. Okay. So we tried to go for looking for different devices which were not TFETs, and there also we found very considerably and reasonably acceptable matches between our results and the results which they have. Okay, so basically we developed a model which can work with any kind of device for predicting basic RTN. We are not saying that it can predict any kind of RTN, three level or 4 level traps. For 2 states, it can predict RTN directly from simulation, and you can have certain parameters. Okay. Okay. Now this is the final part of this talk. So, and this is also an application which we are designing. Okay. Now, if you observe this part, and if I designate this as zeros and ones, okay, then I can use this signal for random number generation. Are you getting my point? Since these instants are random, so I can use these highs and lows for random number generation. And why is random numbers? Why are random numbers important? Application. Random numbers application. In key, and any very popular application which you are using these days. Yes. Cybersecurity more relevant application. OTP generation, very good. OTP generation. While coming also, I paid the driver using OTP, isn't it? So OTP is one of the areas where random numbers can have direct and very simple impact. You do not need very high security things. You can also develop simple applications where you can put an OTP and do your setup. Okay. So RTN, we tried to use this RTN as an OTP generator, basically as a random number generator first. We are working on making it an OTP generation. Okay, but there are certain constants. It is not that easy. The main part is that if your random number has to qualify as a random number, it has to pass through a certain set of tests. Okay, so that you can. There are two types of tests. So the most important one is the NIST test by, I think, Ministry of Commerce US. Okay, so that is the most widely used ones. So they have 16 or 15 tests, and it has to pass at least 50% of them. Any kind of, you can say, random number generator if you are making. Okay, so we tried to do this for both the devices, and I think in one it passed 11, and in the other it passed, I think, 10 or 12, something like that. Okay, so basically this is okay to be a random number generator. Right? So if you observe the timeline, we started with single trap just to see whether single trap can have an effect. Then we found out that due to single trap you can have RTN. Then we realized that okay, using RTN we can go for random number generation. And since this was like you cannot simply convert it, we also did this kinds of tests. Okay. So this is the application which we are doing. So in our lab, we have like any kind of equipment. So for example, a 3D printer, right? So basically, you need to maintain a log for your 3D printer, and eventually it happens that students, they may come, they use it, and while using it, the spool goes bad, they leave. The next person who comes, he finds the spool to be bad, and then since he was using it, I will think that he has spoiled the spool. So there is no definite kind of a log in the system. So we tried to create this log by creating an authentication system for the 3D printer that we have, and it is in the process. So before moving to the hardware, we are trying to look for the software parts, if it can receive the OTP and if it can validate it. And this is the interface that we have for the software part, and we are going to expand it for the hardware. Okay. This is the initiative that I run, okay, the Brixa Lab. And a few days back, it also got registered as a startup. So, and now they are working towards developing products. And this is one of the application which we developed for PhD scholars, which I have shown here while I came back. But since this is a new audience, so this is one, I think. So this is a very simple application. We didn't do anything like very special, but we realized that while doing searches, it becomes very difficult if you are googling your articles, and then suddenly your WhatsApp message comes and you go there and again you start chatting, you do not come back. So we try to put a dedicated system where you have searches for IEEE and all the relevant, you can say, publishers. You can also put notes with your URLs, and you can share it with your supervisor, which you may not do, and also with others. Okay, so that is one option. And we also have upcoming conferences for your under Elsevier and IEEE. So this is just one place where we have brought everything. Since we did not have this kind of apps when we started looking into the, you can say, we started researching on that. So we built this, and you can also check if you have an authenticated journal in your Web of Science indexing and others. So we try to do this. They are very simple, you can say one-stop application. There's nothing great that we have done, but just we have put everything in one place. Okay. And there are also notes you can do. You can also share with anyone. And this sharing is like you can go cross-platform. You can go for WhatsApp, email, anything. So this is like this one. And you can also send email. This is the team that was working, and this is the feedback. So acknowledgements without which this talk is incomplete. Okay, so my students, my professors, my supervisors. So thank you and stay safe. Yeah, before clapping, any questions? Any questions?
The Intel or any design setup, do they outsource the modeling task to any other agency?
No.
They themselves
Yeah.
modeling the devices?
Yeah. Actually, yeah, very good question. When the modeling which we do, like we start from the poisons and do everything. Industries already have certain set of benchmarks which are already ready for them. Okay, they always go by benchmarks. We do not go by benchmarks. Our benchmark is whether our results are matching with the simulation. That's all. But their benchmarks are whether it is satisfying their thermal footprint or when they are putting it on the chip, whether the device electromigration effects are there. So and other such kind of this, it goes into a longer picture. It is not simply restricted within the device. So that is one issue, and if, like it goes through a certain levels of like approvals and tests. So one model, They are like, if you develop a model and you are putting some parameters, it may not like satisfy all the needs of the panelists which are there. Then they are going to ask you to redefine the model, and you'll have to put some empirical parameters there. Therefore, you see in your BC models, you have lot many like empirical parameters, like BCM 64, BCM, like in those models, you see many empirical parameters there. That is the reason.
Like earlier times we used the square root of models for the transistor. Now the fitness are having some very advanced models for their.
Yes.
So what are the new models they are doing?
Yeah. Yeah. So now you see the models which I showed. There are two types of results that you can get from a model. One is the open form of expression, and the second one is the closed form expression. Okay. Now, open form of expression is some expressions where you cannot have a standard equation format. Dependent variable on left side, independent variable on the right hand side, the equation is complete. Normally, you do not get this for standard devices. So therefore, we are using the simulators where you have actually numerical simulations going on. You create a mesh, you define the boundaries, and then it goes. But interestingly, if you are going, the reason we are developing models is not simply to understand its physics, but to use those models in circuit simulators. Therefore, BSIM is so popular because the only reason you are doing a modeling because it has to get used somewhere, and those are circuit simulators. And circuit simulators, you are doing the model for only one device, but in a circuit, it is going to run that model for say 1,000 devices. So just imagine the complexity it has to go through. So therefore, for circuit simulators, it is always preferred that you have a closed form expression. So earlier it was square law, but now we have these different kinds. Even the BC models are directly used, and these BC models are so good that even if you have a thin film transistor, actually for which it was not designed, there also it fits these BC models that you have by altering the parameters by doing that with these. Any other questions?
Does sometimes it happen that you cannot model a device, then
No.
you have to always go from practical side, you have to do the.
Yeah. Means see, you cannot simply like start with a model. There has to be some device or there has to be some groundwork based on which you are going to model. You cannot just give out a theory for a device which has not yet been like fabricated or simulated. It is very difficult. I'm not saying it cannot be done because memristors are based on this principle. The originator he gave the theory first in 1970s, and the device got realized in 2008. So there are possibilities, but these are very rare possibilities.